we've learned that force can be transmitted across empty space. And as the force transmits, it can oscillate to different numbers, different strengths. So the light, we've learned, is nothing more than an electromagnetic wave. There's an electric force that's oscillating as it travels through space, and there's a magnetic force that's oscillating as it travels through space. And together they make light. But there are other things made up from the same stuff. Electromagnetic waves make a ton of different things. In fact, there's a full spectrum, we say. So the spectrum includes things like radio frequencies. Those are EM waves at really low frequencies. And radio frequencies, that's the technology that cell towers use. Your cell phone communicates using radio waves. AM and FM radio stations use the same thing. Even Wi-Fi, Bluetooth, that uses radio waves. Next, we could look and say, oh, well, there's also microwaves, which is what you see in microwave ovens. There's infrared, which is kind of like what, when you turn on your heater, right? It emits, your radiant heater, it emits infrared. Our bodies emit infrared. Then we've got visible light, which is, look at that, what a small sliver of the full spectrum. So our eyes are only attuned to see a small portion. That's what the sun emits. We have ultraviolet, right? Those appear in something called arc welding, where you're joining two pieces of metal together. We have X-rays, soft and hard. That's kind of up along through here. That's what we use to do scans of the body. And finally, we have gamma rays. Those are really dangerous. That's part of what gets emitted from radioactive decay. So when you talk about how nuclear power stations are dangerous, one of the things we're worrying about are the gamma rays that get emitted. As we move from left to right, we increase in frequency, and we increase in energy. Let's write this down. I have a nice mnemonic I like to use to remember this. Raging Martians invade Venus using X-ray guns. So raging, that's radio waves. Then we have microwaves. Next is infrared. Then we have visible light, ultraviolet, X-rays, and gamma rays, the most powerful of all. As we move down, we are increasing in frequency. And as we move down, we are increasing in energy. All electromagnetic waves travel at the same speed through a vacuum. That's not too surprising, right? Because they're all traveling through the same electric field and magnetic field. The forces are traveling through empty space. And so as long as they're traveling through the same medium, empty space, which isn't really a medium though, they have the same speed. The speed of light is 3.00 times 10 to the 8 meters per second. That's 300 million, roughly. And that is the speed of light in a vacuum, but it's the speed of all electromagnetic radiation. This is how fast gamma rays go. This is how fast microwaves go. It's how fast visible light travels. All of these travel the same speed through a vacuum. And a vacuum is just a fancy word for empty space. So let's take a look at a problem. The radio station, 99.7 FM, transmits radio waves at a frequency of 99.7 mega, that's 10 to the 6, hertz. The number that you tune your dial to is the frequency that they transmit along. When you take your car and you turn the dial, you're telling your car antenna which frequencies it should listen for. You're saying ignore all of those other waves, focus only on the ones with this frequency, ignore the longer ones, ignore the shorter ones, only focus on the ones with exactly a frequency of 99.7 times 10 to the 6 hertz. And that's how you tune out the other stations, even though their waves are hitting your car. That's pretty cool. The number means something. Okay. Find the wavelength of these waves that travel through a vacuum. And we're going to assume they're traveling through a vacuum, they're traveling through air, but the speed of light is pretty close in air as a vacuum. Okay, here we go. We know c, speed of light, in a vacuum. We're looking for the wavelength, that's lambda. We use the wave equation. I'm going to plug in for c, the 3.00. Frequency I know, that's 99.7. A hertz is the same as 1 over a second, so I'm going to show this just to illustrate how the units work out. And look at this. On the left side, I have divided by seconds. On the right side, I have divided by seconds. So lambda is going to be 3 times 10 to the 8 over the 99.7 E6. The unit there is going to be just meters because the seconds cancel. And let's calculate this. 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6. I think I missed a 0, 100. Yeah, it's supposed to be this. If you calculate correctly, I forgot 2 of the zeros in the numerator, so I had to multiply by 100. It's 3.01 meters. So think about a meter stick, right? How long is a meter stick? Get 3 of those. That's how big the waves are from perhaps your favorite radio station.